Okay, let's go to the question of Bharadwaj. Because I, anyway my slide also starts there only. I start sort of in the middle, you feel, because I'm going to start with the cash performance equation. So his question was, in Bhaskaran Raman's video, he talks about the processor stalling when it does not find the specific word you're looking for in the cache. So his question was, does it really stall or does it fetch another process to work on? So I was asking, what about your process state diagram? You're in running state when you are talking about fetching data from the cache. Yes.
Yes.
So if there is a cache miss, what does your process state diagram tell you happens?
It means we have the process CPU and but memory isn't there. So
No, you can't say memory isn't there. It's not in the cache.
yes, the process is in ready state because
No, the question for you is, if you say the processor tries to work on some other process, it is a process context switch. Yes.
yes,
When does a process get kicked out of running state? Think of your process state diagram. When does your process get kicked out of running state?
uh, when it's waiting for an IO or when uh,
When it issues an IO command, it moves into block state. Yes. Otherwise, there are two more arcs going out of the running state.
yes, one is the exit state, another one
Yes.
is
So
the
terminate.
IO state,
So if it
termination.
issues an IO, it goes into block state. If it
Block
finishes, it goes into terminate state.
state.
And
And indirect.
yes, when interrupt occurs, what will it do? Where does it go when there is an interrupt?
The process goes into suspend ready.
No.
Okay, timeout. uh,
Timeout is also an interrupt actually, because the timer, when it ticks down and the timer becomes zero, then there is an interrupt. So that's also an interrupt. Where
When
does it go on interrupt?
it goes back to ready again.
Ready state. Okay, so there are only three paths out of running. You go
Running.
to
Yes,
now, because you don't go from running to suspend state directly, to my
yes,
knowledge. You go from block state to
to
suspend state,
suspend it. Yes,
from
yes,
suspend state to ready suspend, and from ready suspend to ready. So
yes,
running, you go to ready whenever there is an interrupt, terminate whenever you exit the process, and you go into block state when you do an IO.
yes,
Now, when you are looking for a word to bring in and you're looking at the cache, Does it satisfy any of these conditions? It's obviously not a terminate.
Yes, ma'am.
Yeah.
And there is no event waiting. No, okay. Yeah.
It's not an IO because you are
Yes,
looking at
yes, ma'am.
memory. In fact, the
Yes, ma'am.
fastest memory that you can find.
Yes, ma'am. Yes.
So,
So it has to go into time. I mean, the interrupt.
if there is an interrupt, but accessing memory is it an interrupt?
Accessing cache might not be interrupt.
Nothing is an interrupt in the main memory. Interrupt is basically when you have IO, right?
Yes, yes, ma'am.
Primarily, it is IO only which it keeps interrupting you, or the timers which will be interrupting you. Okay, clock tick interrupts will be there. Okay, in fact, that is a very most often interrupt that happens because the clock interrupts are very often. But then IO interrupts are also very often because you keep receiving a lot of network traffic as well as the user could be typing something. So every letter you type is an interrupt. Okay. Though your console driver, the keyboard driver, may not send one character at a time too many times, but it generally sends one character at a time. That's why it's a character device. Okay, so there is no interrupt when you're accessing memory. Okay, so what does it mean? It means that the processor is having its time quantum, okay, in round robin scheduling. It hasn't run out of its time quantum and it's trying to get the word into the register to operate word or byte or half word or whatever. Okay, it's trying to get its data into the register to do the operation. So if you didn't have a cache, what will happen? Tell me.
Then we have to check out the main memory.
Yeah, so basically, if you so far you learned about caches in COA, yes? You said yes. You have learned about how do you fetch data from memory into the, and execute in the processor. I mean, how does that happen? COA and OS will give you an idea of how data is being fetched. Now, if
Yes,
you
ma'am.
introduce cache into the equation of fetching from memory, that's all you need to think about, right?
Yes,
So you fetch data normally, you think when you say fetch data, you are thinking you are fetching it from the main memory because in operating systems, at least I don't talk about caches at all. Does sir talk about them? Because when we draw the diagrams, we draw this huge memory which represents main memory and say we are fetching, the process is here, the
yes, ma'am.
process allocates a page here, and, the segment here, and so on. We don't talk about
That is
caches when
that.
we are
Yes,
talking
ma'am.
about memory allocation and all, do we?
No, ma'am.
Yeah. So now we have to combine that aspect with caches. Okay. So, let's look at what happens when you run a program. When you run a program, if it is pure demand paging, then not even one page of your process is brought into memory. Okay.
Yes, ma'am.
But generally, no operating system follows pure demand paging because that leads to unnecessary page fault. So, it does bring a certain amount of certain number of pages into memory without any question. And most of our Programs are very small nowadays compared to the RAM, because if you look at our RAM today, 4 GB is the complete virtual memory of a 32-bit processor, and many of us nowadays have 8 GB RAMs.
Yes, ma'am.
So it can you bring in the whole program into memory without any problem most of the time. Still, let's assume it brings only a few pages into the main memory. Then, when it starts executing the program and it starts fetching in the instructions, and from the instructions it starts fetching the data, then it'll actually have to copy that information into the cache.
Yes, ma'am.
So, after, very first instruction it tries to fetch, there is a cache miss, right?
Yes, ma'am.
So it has to go to the main memory and bring that block into the main, cache.
Yes, ma'am.
Okay. After that, it will fetch from the cache into the register and start executing it. And because of spatial locality, your assumption is your next instruction will be in the cache now. It will not
Yes,
be a
ma'am.
miss. Okay. So basically, that's what happens. So, but when it tries to get data, instruction or data from the cache, and there is a miss, then the way they try to do is cache. You would like it to have as close speed to the processor as possible. So you would like that if there is a cache hit, the the hit time, right? The time to fetch from the cache into the register is 1 clock cycle.
Yes, ma'am.
This is what you would like. That is it possible? Is it not possible? That's a different question. We will not worry about that. Most of the time, the assumption is that the cache is so fast that fetching data from the cache into the register takes 1 clock cycle. But if there is a cache miss, you have to go to the main memory. And main memory takes around 200 clock cycles, 200 to 300 clock cycles. Okay. So now those 200, 300 clock cycles, what do? You have no choice but to wait. That is in a regular, normal processor that we are talking about. We'll go, in complexity of the processor one by one. So at this point, the processor that we are looking at, it's trying to fetch data from the cache and it cannot because the cache doesn't have it. And the main memory has some 200, 300 clock cycle latency. So for that much time, the processor will not be able to do anything but wait so that the data or the instruction block is brought into cache, and then you will be able to fetch it from the cache into the register and then proceed with your implementation, right? I mean execution.
Yes,
So
ma'am.
at this point, it does not actually switch over to any other process because 200 clock cycles, it sounds, oh, 1 clock cycle for cache, 200 clock cycles for the main memory. Oh my God, you feel. But 200 clock cycles are nothing, right? In this way, days of gigahertz clocks, they are very, very small. It's a very small amount of time, actually. So, I mean, basically, when you say 3 gigahertz clock, what does it mean? It's 3 into 10 power 9 clock cycles per second, right?
Yes, ma'am.
So, 200 clock cycles is what? It's nothing.
Yes, ma'am.
So, you'll wait and wait to fetch and do it because the time quantum will not be in terms of that sort of picoseconds or something. It will be usually in terms of at least microseconds. Okay. So I hope that answered the question.
Yes, ma'am.
All right. So let's come to, what. What do you understand of direct mapped cache versus set associative cache, and what are the advantages of set associative cache and so on? Because unless you have that in mind, what do I do?
In direct map cache,
Why there is no other person in this class, is it? Who wants to talk? I can always call out names if this is how we are going to be.
Ma'am, direct map has the index text is calculated and the memory and the word from the memory is put in the cache block with the same index. With the same index.
How is the index calculated?
uh, mm,
Mem-
memory address in main memory modulo the number of blocks in the cache. Uh, or like if the number of blocks are in power of 2, then we take the few bits of uh, the main memory, the address of the.
So let me see. There are about five or six people who haven't seen this direct mapped cache example. All the others have seen. So I'll appreciate if somebody else starts talking too. Especially because the explanation was very well given, nice example.
Okay.
Unlike me, the person is very patient, goes through step by step example. I never do such things. I'll do halfway and say, okay, you know how it will work, sort of a thing. I get very impatient to do that. So, okay, Farzin.
Uh, yes, ma'am.
So tell
How the
me
mapping
what,
is done?
sorry.
Yeah, 1 second.
I think
Yeah,
you
yeah.
have seen it only, of course, only once, but once is enough if you have seen it. If you have not seen
Yes,
the
ma'am.
video, but you just accessed it, then yes, I don't know how. But
Yeah, I have
so
seen it,
how
ma'am.
does how does a direct map cache calculate the index?
Um, so it uses modular operation with respect to the number of blocks
Okay.
for
What about
memory.
set associative?
Set associative, I think modular operation with respect to number of sets.
Okay. How do you get the sets?
Um, how do we get set as in?
So you're saying I'll take the, address modulo number of sets will give me the number of the index, right?
Yes, ma'am.
We divide the total memory by block size.
Uh, and
That will
Yeah.
give us number of sets.
in
If you
case of
divide the,
associative,
yeah, Pranav, if
Set
you divide the cache size by block size, what do you get?
number of
We get number of sets.
You get number of sets or number of blocks?
blocks.
Oh, number of blocks.
It depends on the number of blocks in a set.
Yeah, Tara?
Like it depends on the number of blocks in a set.
Okay. So how do you get how many blocks are there in a set? What's the term for that? What's the term for a set associative cache that gives you a clue about how many blocks are there in a set?
The block. Okay. The block.
Like they say KV associative.
Hmm.
So
So,
KV means it's like K blocks in a set.
okay. So when we say some k-way associative or n-way associative, then it means that there are k blocks in a set, and then you will be able to get the number of sets, right? And the number of sets will tell you how many bits are there in the index.
Yes, ma'am.
Okay. So that's basically, you have to know at least the basics of associative and set associative. What is fully associative?
Anything can be mapped to anything.
Yeah. So in direct map, there is exactly one block into which you can map, right? You cannot place it in any other block. In n-way set associative block, caches, what you can do is you can map into any of the blocks of the set, right? Because you map the block to a set, and you can, actually be fit it into any of the blocks of the set. In fully associative, you can fit it in any block of the cache. Okay. So fully associative is the most, it gives you the maximum freedom, but at the same time, there are some problems with it. What are the problems?
Increase in the hit rate.
Hit rate, problem or good?
Like there is an increase in the hit rate because hit time due to the like it need to search the address. It need to compare the tags value.
Right. So, what is a tag? Because those examples I thought made those parts very, very clear.
Tag is to check whether the is it the same memory block or not, which we are trying to.
Right. So, your address is divided into what parts?
Uh, into tag and
Tag
tag and
index and
offset,
offset.
Yeah,
index and
Brahmani.
offset.
Wait, Brahmani.
Yeah, tag index and offset.
Tag index and offset. Right. So, what is offset?
Offset identifies which where the cache is lying, where the location of that particular word within the cache.
Within the block, not
Yeah, within
we
the
are
block.
talking about the whole cache anyway. Right. So, offset will tell you basically which word within a block you are accessing, right? So how many bits does an offset have? The offset number of bits in the offset is dependent on what?
Like the number of words in a block.
Number of words in the block. So basically, block size will determine the number of bits in the offset, right? Just as the number of bytes in the page will determine the page offset in your virtual address, the number of bytes in your block will determine the number of bits in the offset. Okay. Then you have index. Basically, it depends on how many blocks are there in the cache. If you're talking about direct mapped cache, How many sets are there in the cache if you are talking about a set associative cache? What about fully associative cache? Number of index bits in a fully associative cache? Let me repeat the question. How many bits are there in the index of a fully associative cache?
Zero.
Huh?
Zero.
Fazil?
Is it zero?
Yeah. It is zero because there is no specific cache to which you will be mapping, right? So, you can think of basically it's a set associative cache where there is only one set sort of a thing, right? So there's zero bits in the index. The rest of the bits in the address will be the tag, right? Where you will compare that value with the value you are searching for, so that if there is equality in the tag part, then you have a match. Otherwise, you don't have a match. Therefore, it will be a miss, right? In addition, you also need to know whether the particular block in the cache is valid or not, meaning that does it contain meaningful data, or it's just nothing which has been filled at all, either not filled, or it was filled by an earlier process which is now invalidated and you have a new process running, so all the cache pages need to be invalidated, right?
We have a valid.
Yeah.
No, like we have a valid picture.
Mm. So we have a valid bit to determine whether the particular block is valid or invalid. So there are two things we need to do for to determine whether it's a hit or not. We basically take the index bits and index into the cache. Then if it is set associative, we have to compare multiple tags to the tag of the address we are looking for, right? If any of the tags of the blocks in the set matches, and it is a valid block, then we say there is a cache hit. Either if the valid bit is not set or the tag does not match, then we say it is a cache miss. Okay. Any questions on that? Like I said, I'm not really in the videos are very good at explaining how it works. So I'm not doing any of the slides or anything because we have such good videos there. Okay, any questions? What else did you learn from the videos, whoever has watched them? What did you learn new, or what did it clarify that was not clear to you earlier? I would like to hear that.
Ma'am, implications of increasing block size and how to reduce miss penalty when we do that.
Okay, and that is from Bhaskaran Raman's thing.
Yes.
Okay. Why does increasing block size increase miss penalty, you're saying? Is that what you feel was clarified better for you?
I think I didn't think in that way when I was doing COA, but now I understand why increasing block size has some advantages and disadvantages. I didn't know that we had some disadvantages when I was doing COA.
Okay. Okay. Anyone else?
This did revise the COA part, ma'am. Like I, though it was taught in COA, I didn't remember it,
Hmm.
but now I kind
So
of
you
understood.
did all of Bhaskaran Raman's stuff also in COA?
I don't think so, ma'am. Like I remember cash being taught, but I didn't. I don't remember this all. Maybe it's taught, but
We didn't do the analysis part, ma'am. We just learned about them.
Yeah, yeah. Analysis, yes, probably very
yes, ma'am.
unlikely. But I thought Bhaskaran Raman's final video, Cash Performance, actually also talks about many optimizations. Did you cover all of them too?
No, ma'am.
No,
Some parts I thought, because actually some parts of that video go into chapter 2 of the book we are looking at, which is advanced cache optimizations. What we have in the appendix B are basic optimizations. So, do we want to take a break or continue another 15 minutes or so and then take a break? What do you want to do?
anything is fine.
Yeah, we can
Like,
continue.
I'll share screen and stop after a while, maybe, because. Okay, so like I said, I'm starting in some sense probably in the middle of caching. It feels like, though it's not exactly. I am reviewing some parts of the videos, especially the videos of Bhaskaran Raman. Okay. um, because I felt the most important thing I wanted people to do as preparation for this class was to watch the first three videos I have put up, right? Which is memory hierarchy, direct map cache example, and set associative cache example. I thought the set associative cache example was very very clear in what are ways, right? What are the ways, and showing how and why the cache hit becomes much better with the two-way set associative cache that it describes,
Yes.
right? Okay. So, based on the assumption that those are done, I am starting somewhere else.
Okay.
So this goes anyway also to the question that Bharadwaj asked. So CPU execution time. How ma'am has talked about CPU execution time in the class, on the first chapter, right? The quantitative principles, basically. So the CPU execution time is CPU clock cycles into clock cycle time is what you learned in that chapter. But now we have to add memory stall cycles to the CPU clock cycles also. So a process execution is not just a question of the number of processor cycles that we are using, but unfortunately the processor stalls in between to get information from memory. So when we are talking about cache performance, we are also talking about how many cycles lead to memory stall cycles, and all these are added to the clock cycle time. Okay. So how do you calculate memory stall cycles? The number of misses that you have into miss penalty, where miss penalty is always given in terms of how many clock cycles does it take, right? Miss penalty is basically the time it takes for you to access the main memory. And so number of misses can be, then talked about as instruction count into misses per instruction, right? And then you basically expand it even further and say it is instruction count into how many memory accesses do you do per instruction into the miss rate, into miss penalty. So this is the final equation for memory stall cycles, and this is the equation which is easy because instruction count can be measured, right? Once your compiler finishes compilation, you know how many instructions are there in your program. So the instruction count is known. Memory accesses per instruction based on the instruction, right? You know whether it is accessing, you anyway have for every instruction one memory access minimum, right? One memory access. Why? Because you are accessing the instruction itself. So you're fetching the instruction, so that is one memory access, right? But when you decode the operation, that it can be a register operation, right? In which case you need to fetch probably two operands from the memory. It can be a immediate operation, which means you need to fetch one operand from memory, and so on. Okay, you may have to do load or store, in which case you have to do one data operation to the memory. So based on the instruction, you know how many memory accesses you will do for that instruction. Okay, so on the average, what are the number of memory accesses per instruction that your program is doing? This is also therefore known. It's not something that you have to guess, right? Miss rate can be calculated, right? Because you can have the processor actually maintain a counter where it sort of gives you how many misses happened in the cache, which you can read off the processor. So miss rate can be actually read off the processor. Processors nowadays do lot of work in terms of maintaining counters, which are useful for statistical measurements of various parameters of execution. Okay, so that those can be used for optimization by compilers. People are also using machine learning algorithms to improve performance of operating systems and so on. So you do need the statistical information, and processors are maintaining comparatively some amount of statistical counters. Okay, so miss rate can be like that. Miss penalty is known, right? Because you know how many cycles it takes for you to read off the main memory. So when you look at the last version of this equation, it's basically every term is known or can be measured easily. Okay, so this is the most favored equation for determining how many memory stall cycles overall does your program result. Okay, any questions on that?